So last day we started, to look at Nether Theorem, and in order to do that, we needed to define what a symmetry transformation is, which is a transformation of all the variables, including time, all the generalized coordinates, and also time, so that the action remains invariant. So the statement that the action remains invariant is written here. So the action, remains in the same form, in the same functional form. And then we started to see, what conclusions can be derived from this. And the first conclusion, the first consequence that we saw is that there is something that we call a symmetry condition, right? This is a symmetry condition or symmetry test, which, will be something more familiar once we apply it to a case that we know better. Okay, so instead of doing it in general, once we apply it to a simple case that we are more familiar with, we'll see what this symmetry test or this symmetry condition amounts to, what this symmetry test tells us. But apart from this, we also, and this symmetry test, this symmetry condition is something that has to be satisfied for the action to be invariant. Okay, so this has to be true for the action to be invariant, without using the equations of motion. So just, based on the form of the action only. And then from this symmetry test, the symmetry condition, we are now, looking at what happens when we impose the equations of motion, when we also use the equations of motion. And for that, we had to, to work all this way through until we got to this point, in which we already see that, in some parts of this complicated zero that we are computing, because this zero is the difference between the two actions, which are the same, so that's why it's zero. Okay, so in some parts of this complicated zero that we are computing, we see that the equations of motion are emerging. So like, for instance, here. But there are other places in which it's not so obvious. And one of the places where it's not so obvious is this, red star that we have here, and that we promised that we would compute today, okay? And that I left it as an exercise. So that's what we're going to do now. Now we're going to compute explicitly this red star, and we're going to see what it amounts to, what it is, okay? And we see that even though it is not completely obvious written in this form, it's actually, something, very similar. Actually, it's the same as the equations of motion, basically. So let's compute this thing now. So in order to compute this thing, okay, we just write the first term, dl dt, that we leave it as it is. And now we start taking derivatives with respect to time of the whole term inside the parentheses, okay? Now, we have to remember, let's put it here, that the Lagrangian is a function of q, which is a function of t, a function of q dot, which is a function of t, and then maybe is also an explicit function of time. So now we have to take the derivative of this. So let's go step by step. So that now is the derivative of this product minus the total derivative of the Lagrangian, okay? And so this is the partial derivative of the Lagrangian with respect to time. Partial derivative refers to this dependence only. And now plus derivative with respect to time of this product. So that's a derivative with respect to time of the first term times the second term plus the first term, plus the first term, oops, times the second term, which is q double dot, okay, minus the derivative with respect to time of the whole Lagrangian, okay? So now let's keep on computing. So this is dl dt plus, now I have to take the derivative with respect to time of the derivative of the Lagrangian with respect to q dot, okay? So that means that I have to take the derivative of this thing, okay, And this I'm going to leave it as it is. This I'm going to leave it as it is. Wait a second. Yes, I'm going to leave it as it is. Okay, so this is derivative with respect to time of the derivative of the Lagrangian with respect to q dot times q dot plus the derivative of the Lagrangian with respect to q dot times q double dot minus, and now I have to take the total time derivative of the Lagrangian. So that is derivative of L with respect to q, derivative of q with respect to time, which is q dot, minus derivative of L with respect to q. I said q. Derivative of L with respect to q. Derivative of L with respect to q, derivative of q with respect to time, which is q dot, minus the derivative of L with respect to q dot, the derivative of q dot with respect to time, which is q double dot, and then minus the derivative of L with respect to t, right? So that's a chain rule. That's a chain rule applied to this derivative. I have to take the derivative with respect to time, and there is time derivative here, here, and then the explicit time derivative. So it's dl dq dot minus dl dq dot dq double dot minus dl dt. Okay? So now we see that this term cancels that term. Okay? And also, this term here cancels this term here. And then what happens? That, surprise, surprise, what we find is that this is the same as dl dq, so this term here, minus d dt dl dq dot, the whole thing multiplied by minus q dot. You agree so far?
Yes.
Okay. Any questions?
No questions.
Okay, good. So now that we computed, red star, we can close this parenthesis and go back to that zero. So that zero now is going to be integral over time from t1 to t2 of, well, now we computed, red star, and red star is also proportional to the same equations of motion I also have here. So that means that I can write this thing as dl dq. Then today I have problems with this q. dq, okay, minus d dt dl dq dot. I already had a delta q, and now I'm adding a minus q dot times delta t. Okay, so that is the first two terms. The first two terms happen to be proportional to the equations of motion, okay? And then the rest, plus integral dt from t1 to t2 of d dt partial of L with respect to q dot delta q minus dl dq times q dot minus L delta t plus delta g. This is the whole thing. So if now we apply this condition on the solutions to the equations of motion, that means that on this is zero. So let me just, signal it. Really, this is zero on the equations of motion. So therefore, on the equations of motion, on the solutions to the equations of motion, remember that is what we also define as being on shell, and this nomenclature is used in some books, we find that 0 is, let's go back, this integral right here, right? So that means is the integral dt from t1 to t2 of d dt, and now is partial of L respect to q dot delta q minus partial of L with respect to q dot times q dot minus L delta t plus delta g. So this is the condition that we find now on the equations of motion, okay? Now, let's see if we can identify things. Who is partial of L with respect to q dot? By definition.
The momentum?
Yeah, P. It is P, the canonical conjugate momentum, right? Who is this object here in parentheses?
The Hamiltonian.
The Hamiltonian. So what we see is that as a consequence of the symmetry, we find that, you know, this whole thing has to vanish. And if this is true, for any T1 and T2, because the condition of the action being symmetric, of the action being invariant, did not use a specific T1 and T2. It was, you know, a property of the action for any T1 and T2. So then that means that the integrand now has to be 0. So d dt of dl dq dot delta q minus dl dq dot times q dot minus L delta t plus delta g has to be 0, or in other words, that this thing has to be a constant of motion. This combination here has to be a constant of motion. So one way to remember this is to write it as P delta Q minus H delta T plus delta G equals constant. Even though we are using all the time a Lagrangian formulation, which means that, you know, everything in here is written in terms of Q and Q dot. There is nothing written in terms of P, but we could always write it like this if we wanted to. I mean, we're still in a Lagrangian formulation. We are talking about, you know, the invariance of the action as an integral dt of the Lagrangian. But that's an easy way to remember this whole expression, okay? So this is the result of Nether's theorem, and this is a very important result. So this, we're going to frame it, because this is the theorem that ensures the conservation of all the quantities that we all know and love, like energy, you know, angular momentum, linear momentum, and all that, as we will see. So this is Nether's theorem. Which says that for every transformation that leaves the action invariant, there is an associated conservation law. Conservation law given by a star, and this is a star. Okay, but this is very important. Okay, and now we're going to have to look at all the consequences of this conservation law of Nether's theorem. Okay. Okay. So questions up to now.
No questions.
Okay. So let's look at these consequences. So this is going to be symmetries and conservation laws in non-relativistic mechanics. So let's look. Let's look at all the conservation laws that we know, and let's see how they, appear because of a symmetry transformation. So if we're talking about non-relativistic mechanics, okay, now we have to identify which are the symmetries of non-relativistic mechanics. Okay, so this will help us, after we identify the symmetries, will help us, through Nether's theorem, identify the conservation laws. So what are the symmetries that we have in non-relativistic mechanics? What can we do to the system so that nothing changes? And by nothing changes means, the action doesn't change. We can think of transformations that don't change the Lagrangian, or we can think of transformations which do not change, the solutions of the equations of motion. And which are those transformations? So what kind of transformations can you guys tell me that are symmetries of non-relativistic mechanics?
A rotation.
Exactly. Rotations in 3 dimensions. So that's number 2. Rotations in 3 dimensions, right? Because we are in 3 dimensions, three spatial dimensions, right? So that's going to be 3 spatial dimensions. Let's be a little specific. Spatial dimensions. Yeah, absolutely. So that means that I go from R to R prime, which is going to be a matrix omega acting on R. So this is a rotation. Okay. It's a rotation. It's a 3x3 matrix with certain properties. We'll see what those properties are. And now I need to know how many parameters. How many parameters? Number of parameters. How many parameters?
3.
3.
6, I think.
3, 6.
6.
Who can say something else? 3, 6. Why not 9 or 4?
Well, 6 because it has to be the same as its transpose.
So what does it have to be the same as its transpose? So what do you mean? What do you say 6? How you count these 6 parameters? I mean, the number of parameters means the number of numbers, okay, the number of parameters that I have to fix in order to have fixed a rotation. To define a rotation, I need a number of parameters, and this is the number that I'm asking. Okay, is it 3? Is it 6? Or is it something else? So you said 6. How you count those 6? Which are those 6 parameters? Hello? Hello, how did you count those 6 parameters?
Yes, no, sorry. So for it to be a rotation, it has to belong to the orthogonal group. So
yes, exactly. It has to be an element of the orthogonal group.
So yeah. the transpose doesn't have to be the same as the same matrix, but as the transpose has to be the inverse of the matrix.
Okay, has to be the inverse. Okay, good.
So I don't know how many parameters does it leave, but like I don't know.
So we can try to see what happens, right? How many parameters it have, and then also, I mean, it has to be a proper rotation, right? So that means that the determinant has to be 1. So there are all these conditions, but I mean that's not the easiest way to count parameters, and this is why actually the number of parameters is not 6. So I mean the guy who said that the number of parameters is 3, how did you count these 3?
Well, I think there are 3 angles, the Euler angles, that you can make a rotation.
Exactly. So this, yes, this is true. Oops. This is the thing. I mean, what you said, so that's 3 parameters. What you said about, the orthogonal group and all these conditions that the transpose has to be the inverse and blah, 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 all this is true. If you do this carefully, in the end, you're going to see that there are only 3 numbers you have to fix in order to define a rotation. But it's easier to remember that when you guys were doing, the spinning top, right, the peonza, right, this you guys were studying, or the solid rigid, that then when you studied rotations, there were only 3 angles you had to fix, which were the Euler angles. So that's an example. So for example, the 3 parameters can be, for example, the Euler angles. So those are 3 parameters. I mean, you can define a rotation with another set of 3 angles. Doesn't have to be the Euler angles all the time. It can be any other 3 parameters, okay? But it will always be 3 parameters only, okay? And the easiest way to remember is to remember that there are 3 Euler angles to define a rotation for a solid rigid, right? Okay. So rotations. So rotations is a symmetry of non-relativistic mechanics. That's right. That's what says that, in empty space is the same to go left as to go right, to go at an angle of 45 degrees. Good. What else? What other symmetries do we have?
You can change your coordinate origin to any point.
And so what do you call that?
Sorry?
What do you call, changing the origin of your coordinate system?
Well, you can take your system to one place or another, and the physics must not change.
I agree. But what do you call that in mathematical terms? When you change your...
a translation?
Exactly. That's a translation. So that's a translation. A translation of the origin of space. Okay, so that means you go from R to R prime, which is R plus a fixed vector, R0, right? How many parameters do we have here?
3 again?
Yes, 3 parameters. 3 parameters. The 3 components of R0, right? Right?
Yes.
Those are the 3 parameters, are the 3 components of R0. Are those the only translations that we can do?
You can have translations in time.
I couldn't hear.
There are translations in time.
Absolutely. Translations of the original space and time. Right? I mean, whenever we just follow the motion of a particle, it's not important at all when we set the initial time, right? When we just start, setting the clock. So time, the origin of time can also be translated. So that means t goes to t prime, which is t plus t0. So the origin of time. How many parameters? Obviously one parameter, right? t0. Okay, so we have translations of space and translations of time. Then we also have rotations in 3 spatial dimensions. Is that all we can do?
You can do also a boost.
A boost. Good. What is a boost?
When the system goes with a velocity relative to your system.
Right. So a boost is a change of reference frame. Also, I mean, we also call that a change of reference frame. So that means that we just move with a constant relative velocity, relative to the other system. Okay. So this sometimes is also known as a Galilean transformation. Right? Sometimes we also call it a Galilean transformation. And so that means that from R we go to R prime, which is the old R, plus a constant velocity v times t, where v is constant. So that's a change of reference frame, right? And time we don't change. Time stays exactly the same. So how many parameters do we have? For a boost.
3 parameters.
3. Each and every one of the components of this constant velocity, of the relative velocity between the two systems. So that's 3 parameters. 3 parameters. Okay, so that means that the most general transformation is going to be everything at the same time. So that means R goes to R prime. This is an R. R prime. Oh man. R. Which is a rotation plus a boost plus a translation, right? And T goes to T prime. This is a T prime, which is a translation of time. So all in all, 10 parameters. 10 parameters in total, okay? So now we're gonna look at, what are the consequences following Noether's theorem, what are the consequences of every one of these symmetry transformations, right? We're going to look at all these transformations. So let's imagine, or let's assume that we have a Lagrangian, which is given by the kinetic energy, a function of the velocities, and a potential, which is a function of the positions for I from 1 up to capital N. Okay, so I have a system of n particles in Cartesian coordinates. In Cartesian coordinates. Okay, so I can always describe my system in Cartesian coordinates if I want. So I'm going to look at, these symmetry transformations in these coordinates. And let's go one by one. First, let's look at what happens when I time translate, when I make a translation of the origin of time. Okay, so that means that I go from t to t prime, which is t plus t0. Okay, and I go from r to r prime for all the particles, which is the same as ri for all of them. So that's a symmetry. That is the transformation that I'm making. Okay, so this means that the variation of time, remember that I have to identify the variation in time, the variation in q, the variation in q dot, all that, okay? Because that's what appears in Nether Theorem and in the symmetry test, in the symmetry condition. So the variation in time is what in this case? Can you guys tell me? What is delta t?
T0.
Absolutely, T0, very well. Yes, okay. What is the variation of the positions? Ri.
0.
0, because the positions are not changing. And now I need to know what is the variation of Ri dot. And for this, I have to remember, this result, okay? And this I'm going to write here. Recall. I'm going to put recall because we already derived it, okay? Recall. The variation of Q dot equals d dt, the variation of Q, minus Q dot derivative with respect to time of the variation of t. Oops. So this result, we obtained it when we derived the symmetry conditions, the symmetry test, okay? And let's put it here. So that means that now we can compute, what is the variation of r dot. The variation of r dot is the derivative of the variation of r, which is 0, minus r dot times the derivative with respect to time of the variation of t, of time. But the variation of time is a constant t0. So the derivative with respect to time of t0 is 0. So this whole thing is 0. You agree?
Okay.
Yes.
All right. So now, symmetry test. Symmetry test or symmetry condition. We can also call it condition. Symmetry test or symmetry condition. Let's put it like this. Condition. So we can go back to the expression that we got, and it was derivative of L with respect to Ri, delta Ri, and sum over all of them from 1 up to n, plus derivative of L with respect to R dot I, delta R dot I, plus derivative of L, derivative of L with respect to time, delta t, plus L derivative with respect to time of delta t equals 0. That was the symmetry test that we obtained, okay? And now all we have to do is just replace, all these deltas in this expression. So what do we find? So that's going to be derivative of L with respect to Ri, derivative of R, but that, the variation of Ri is 0, so this first term is not there. So this I don't care about. So this one is 0. This one is 0. This is also 0 because delta I dot is also 0. Okay, the variation, the derivative with respect to time of delta t, this is also 0 because delta t is a constant. Okay, t0 constant. Huh? So finally, it is the partial derivative of the Lagrangian with respect to t, which is 0. So this leads to the condition that the Lagrangian cannot depend explicitly on time. But that's something we already saw, right? We already saw that this was, if the Lagrangian depends on time explicitly, okay? No, okay, so let me just rephrase it. Let me just say it in a different way, okay? So the symmetry condition tells us this, that, that the system, the whole system is going to be translation invariant with respect to time if the Lagrangian does not depend explicitly on time. And now we're going to see what Nether Theorem tells us, what the conservation law is, and we already know what the answer is going to be, right? So that's the symmetry condition. And now the conservation law. The conservation law, and that's Nether Theorem, that says that the derivative of L with respect to R dot I delta Ri, sum from I equals 1 up to n minus h dt, remember, this has to be a constant. But in this case, delta R is 0, so this is 0. So this means that h has to be a constant, right? And indeed, this is something we already knew. We already knew that when the Lagrangian does not depend explicitly on time, we know that the total derivative of the Hamiltonian with respect to time is actually the derivative of the Hamiltonian with respect to time explicitly, which is minus the derivative of the Lagrangian with respect to time. So if this is 0, then the Hamiltonian has to be a constant. And that, again, we recover the same result from Nether's theorem now, okay, for something that we already knew had to happen, okay? So Nether's theorem in this case already tells us something that we already derived, when we saw that there was this chain of equations. Do you agree?
Yes.
Okay, so that was translation of time. Now, translation of space. Translation of the origin of space. Okay, so that is for each position, we just shift it by a constant vector R0. R0 constant. And we don't change anything else. So t goes to t prime, which is the same as t. Okay, so that means that delta Ri for all of them is R0. That's for all the particles from 1 up to capital N. Then delta t is 0 because we don't change time now. and delta Ri dot. Remember that delta Ri dot is the derivative of delta R minus R dot derivative of delta T, right? So it's the derivative of delta R, so that is 0 because delta R is R0 is a constant, 0. And then the derivative of delta T is also 0, so that whole thing is 0. So that's it. So those are the the transformations, the changes that we make in the variables. So again, symmetry test. Symmetry test is the derivative of L with respect to Ri, delta Ri, sum from I equals 1 up to capital N, and then there is nothing else. There is no delta T, there is no nothing, okay? So that means that this thing has to be 0. But of course, this is the same as the derivative of L with respect to Ri, and delta Ri in this case is R0, and this is the scalar product, the dot product, sum from I equals 1 up to N. But what is the derivative of L with respect to Ri? If I have a Lagrangian, remember that I have a Lagrangian, which is kinetic energy minus potential. So what is the derivative with respect to Ri?
Pi dot,
Um,
the conjugate momentum. But
yes, this is true, but just look at this expression. Yeah, what you said is true, but it's going to look more familiar if you look at this expression and you take the derivative with respect to Ri.
the force.
Exactly, is the force. So R0 does not depend on I can pull it out. So this is R0 dot the sum from I equals 1 up to N of the force acting on the ith particle. This is the force acting on the particle number I, if you wish, right? So that means that I'm summing all the forces acting on each and every one of the particles. So that means that this is the total force. So that means that this is R0 dot the total force. And this has to be 0. Okay, this has to be 0. So that means that in the direction of R0, there can be no net force. That's what this equation says. In the direction of R0, there can be no total force, no net force. All the forces have to vanish in the direction of R0, right? That's what this thing says. So the fact that the system is invariant under translations in the direction R0 means that the total force in this same direction R0 has to vanish, right? Do you agree?
Yes.
So now the conservation law. What does the conservation law says? What does the Nether Theorem say? So this is the sum from I equals 1 up to N, derivative of L with respect to R dot I, times delta R dot, delta R, which is R0 in this case, and everything else vanishes. This now has to be a constant. That's what Nether's theorem says, that this has to be a constant. Now, what is this? What is the derivative of L with respect to R dot for each particle I?
Pi.
Exactly. In this case is the linear momentum, pi, or in general it would be the canonical conjugate momentum, pi. So that means that R0 times sum from I equals 1 up to n of pi has to be a constant, but the sum of all the linear momentum p of each and every one of the particles is nothing but the total linear momentum. So that means that R0 times p total has to be a constant. So what this, the net result is that if the total force in a certain direction R0 vanishes, then the total linear momentum in the same direction R0 has to be constant. Now, if the system is such that this R0 can be in any direction, so it can be in the x direction, in the y direction, or in the z direction, then the total force, not in one direction, but in all directions, has to vanish. And then the linear momentum, the total linear momentum as a vector in the three directions has to be constant, right? But this, in this case, we can derive a more precise theorem, right? Which says that, if the total force in a certain direction vanishes, then the total linear momentum in the same direction is constant. All right? So that's a result. Any questions? Now we're going to do rotations. Any questions?
No.
All right. So now, rotations of space. 3. Spatial rotations. Okay? So that means that each position vector, we change it by multiplying it by a rotation matrix, okay, omega. And so this, we have to see, what this rotation matrix omega is infinitesimally. Remember that we are only interested in infinitesimal changes. So that's going to be the same vector as before, plus an infinitesimal change of r. So this is infinitesimal now. Infinitesimal. It's an infinitesimal rotation away from unity. And t does not change at all. So t stays the same. And this is true for all the particles. Okay? So that means that the variation of each position vector is precisely this infinitesimal rotation. Infinitesimal rotation away from unity, because this is the variation with respect to doing nothing. So that's going to be omega times Ri. Now we'll see, an explicit expression for this omega in one case. And then delta Ri dot, this is the variation of delta. This is just the derivative of this thing. So let's go back to the to this expression that we have here. The variation of r dot is the derivative of the variation of r minus r dot times the derivative of the variation of time. Okay, but the variation of time is 0 because time doesn't change. So this is omega times the derivative of this thing, just like that, with the same omega, with the same omega. All right, so again, symmetry test. Symmetry test. And the expression for the symmetry test is derivative of L respect to Ri, delta Ri. Let me write it down. Sum from 1 up to n plus derivative of L with respect to Ri dot, delta Ri dot. This is a dot product, huh? And this has to be 0 because there is no other variation. Okay, so that means that the sum from I equals 1 up to n of the derivative of L with respect to R. What is the derivative of L with respect to R? We computed it before. We saw it here. Derivative of L with respect to R. What did we say it was?
The force?
Yes, F. The force acting on the ith particle, okay? Delta Ri. Delta Ri is the matrix omega times Ri. Plus derivative of L with respect to R dot. What did we say this thing was?
The canonical momentum.
Yes, P sub I, okay? Now times the same matrix omega times R dot I, okay? And this has to be 0, okay? So that is the symmetry test. Now, let's work out what the symmetry test says in one explicit case. So this is in general, right? But maybe this way doesn't look very familiar. And so let us look at what this condition is within an explicit case. Explicit case. So that means that I have to identify what this matrix omega is. So the explicit case that I'm going to look at is going to be a rotation around the z-axis. Okay? So that means a rotation on the xy plane, right? So I'm going to leave the z-axis exactly the same, and I'm going to rotate x and y. All right, so let's start. So I need to identify which is the matrix omega, which does this, which makes a rotation by an angle theta, let's say, around the z-axis. So this is a 3×3 matrix. And now we have to say which are the entries on this 3×3 matrix. And I know that the z-axis doesn't change. So that means I have a 1, a 0, a 0, a 0, and another 0. I only have to, fill in this 2×2 submatrix. So which is this 2×2 submatrix, which corresponds to a rotation around the z-axis, or if you wish, a rotation of the xy plane? Who can tell me?
I think this matrix is cosinus of theta, sinus, minus sinus and cosinus.
Yes, exactly. It's cosine theta, sine theta, minus sine theta, cosine theta. That's exactly what it is. Precisely. Yes. Okay, but now we have to extract from this omega, which is the full rotation matrix, the capital omega, which is the infinitesimal variation, which means that we have to expand for very small angles, theta much smaller than 1, okay? Very small angles. So that means that I'm going to have 1, 1, 1, 0, 0, plus delta theta, let me put it like this, delta theta minus delta theta, I'm sorry. Here is a 0. 0, 0, 0, 0, 0, 0, 0, right? So that's for a very small angle. Let me put it, delta theta much smaller than 1. Do you agree? And this is plus order delta theta squared. Do you agree?
Yes.
So that means, and this is my matrix omega in this particular case. So the importance property that I learned by doing this little exercise in this particular case is that omega is anti-symmetric. The matrix omega, which measures the infinitesimal rotation away from unity, that's exactly what this is an anti-symmetric matrix. And this is going to be important in the calculation that now I'm going to do. Okay, so remember this fact. Omega is anti-symmetric. So let's go back. Oh, sorry. Let's go back and let's just look at the symmetry test for this particular case. All right. So 0 has to be the sum from I equals 1 up to capital N of each force Fi, my matrix omega, which I just derived, plus Pi, my matrix omega again, R dot I. Okay, good. So this is the sum from I equals 1 up to capital N. And now I'm going to decompose this vector matrix vector into components. So this is going to be a sum from J and K equals 1 up to 3 of the force Fi component J, the matrix entry JK, and the vector Ri component K. That's the first term. Plus the linear momentum I component J, the matrix entry JK, and the vector R dot I component K. You guys agree?
Yes.
Don't get confused with the index that, labels the particle, which is I, and goes from 1 to N, with the index which labels the component, which in this case is J and K, and goes from 1 to 3, because there are 3 components, okay? Now, let us look at this second term. So the second term is the sum from I equals 1 up to capital N of the sum J and K from 1 up to 3 of P. But P is the mass times the velocity of each particle, component J. Then I have the matrix, omega JK, and then I have the velocity again, Ri, component K. Right? How much is this?
Zero.
0, why?
Because the omega matrix is has 0 elements on the diagonal, so the same terms can be multiplied with each other.
Yes, but there are also cross terms, right? There are also terms in the off diagonal. I mean, the matrix omega is not 0 everywhere.
But the omega is anti-symmetric, so one term will be killed with another.
Yes. So right. So the reason why, yes. So okay. So this is 0. I agree. The second term all by itself is 0, and the reason why it's 0 is because omega is anti-symmetric. You have to realize that because omega is anti-symmetric, the terms in the diagonal have to be 0. It's not an independent condition, right? If the matrix is anti-symmetric, the elements in the diagonal have to vanish necessarily. Do you agree?
Yes, I do.
Right? Why?
Because one number that is equal to its negative one is only 0.
Right, exactly. So yes, because the elements in the diagonal equal minus themselves. That's right. So then, so they have to be 0. And this is a general result. Remember that I think that we derived this at some point, that, you know, the contraction of an anti-symmetric matrix with a symmetric matrix, because we can also write this thing as sum over j and k from 1 up to 3, omega jk ri, sorry. Now I'm writing components, so this is ri dot j ri dot k. This equals 0 because this is anti-symmetric and this is symmetric, right? And this in the indices jk is a symmetric matrix. This in the indices jk is an anti-symmetric matrix, and I'm contracting both of them. I'm computing the trace of the product, okay? So that necessarily vanishes. And this is general, this is always true. Anyway, one way or the other, this is 0. So this term here is not there. So this 0, which is the symmetry test, is the sum from 1 up to capital N, sum over j and k from 1 up to 3 of fi component j, omega jk, ri component k. Okay? Now, let us compute this thing with the matrix that we had here. So with the particular example that we had, exactly with this one, okay, with delta theta here in the off-diagonal submatrix of the first 2 entries. So if you make this calculation explicit, what you find is the sum from 1 up to n. Delta theta factors out because it has no index. And then I have fi first component, and then I have ri second component necessarily, because remember that it was anti-symmetric, so the elements in the diagonal were 0, minus fi second component, ri first component. So that's all there is. There is nothing else. All the other terms vanish because omega has a 0 entry in there. So what is this? Well, this happens to be the same as minus delta theta of the cross product of Ri with Fi, the third component, sum over I from 1 up to capital N. So in other words, this is the same as minus delta theta sum from I equals 1 up to capital N of Ni, which is the moment of the force. So this is also called the torque, or the moment of the force in the third direction. And we're summing all of them. So that means this is the same as minus delta theta, the total moment of the force in the third direction. And the reason why is in the third direction only is because this was a rotation, you know, along the z-axis in the third direction. Okay, so that's the symmetry condition. So now the symmetry condition is that this has to be 0. So n total third condition has to be 0. This is now the symmetry condition. So you see that if the system is rotationally invariant along the third axis, that means that the total moment of the force, of all the forces, okay, has to vanish along this direction. Along this direction. Now that we have identified the symmetry condition, we can also go and ask, what is the conservation law that is going to derive from here? And we know what it's going to be, right? Because if we know that a system is such that the total moment of the force in the third direction vanishes, we know that the conservation is going to be that the angular momentum along the same direction in the third axis has to be constant, right? And so that's what Nether's theorem is going to tell us. So let's do this. Conservation law. So the conservation law, remember, is that derivative of L with respect to Ri dot omega Ri, sum from I equals 1 up to capital N. That's all there is. This is delta R. This has to be a constant. All the other deltas are 0 in the conservation law. That's the only term that survives. So that's the thing that I have to compute now. So let's compute it. Okay, so that means that constant, this constant has to be the sum from I equals 1 up to capital N of derivative of L with respect to R dot. So that is Pi. We already saw this several times, times omega Ri. Okay, all right, so this is the sum from I equals 1 up to capital N of Pi component, of Pi component J, omega Jk, and then Ri component K, and this I sum over J and K from 1 up to 3, right, as before. But the calculation, I don't have to do it again. I don't have to do this calculation again because I already did it, right? I already did the calculation here. Remember this calculation. The sum of F comma J, omega Jk, Rik, this thing is nothing but the cross product. So here, I can copy the result and say that this constant also has to be the cross product. So that's going to be minus delta theta, as before, the sum from I equals 1 up to N of Ri cross product Pi third component, exactly as I did before when I was computing the moment of the force, right? Okay, but what is this object? We know what this object is, right? It's minus delta theta, the sum from I equals 1 up to N of the angular momentum, Li of each particle along the third direction. So this is minus delta theta of the total angular momentum along the third direction. So that has to be constant. So this means that L total along the third direction has to be constant. And along the third direction, because it was a rotation along the z-axis. I mean, it is obvious that if I do a rotation along the y-axis, then there's going to be the total angular momentum along the first direction, and along the y-axis is going to be the total angular momentum along the second direction that are going to be constants. Okay, so this is how we recover that, whenever the moment of the force, okay, is 0 along one direction, the angular momentum along that direction is also constant. But we see that there is a connection between the moment of the force being 0 along one direction and the system being rotationally invariant along that direction. Okay? So that's all about rotations. Good. So we have studied, let's go back. We have studied the consequence of translations of time. This is translations of time. Also translations of space, rotations of space, of course. And we have seen when the Hamiltonian is conserved, or if you wish, the energy, when the Hamiltonian is the energy, Hamiltonian, or when the Hamiltonian is the energy, conservation of energy, conservation of the linear momentum, B, conservation of the angular momentum, L. So it seems that we have exhausted all the conservations that we know, right? For a non-relativistic system. However, in the symmetries that we identified for a non-relativistic symmetry, there were translations of time, translations of space, rotations of space, and there were also boosts. So it seems as if there are symmetries, the boosts, that do not correspond to any conservation law? Or is it true that there are conservation laws beyond conservation of angular momentum, conservation of linear momentum, and conservation of energy, and that nobody told us about? You see what I'm asking? There seems to be three symmetries, the three boosts, one for each direction, that do not correspond to any of the conservations that we always thought there would be in a non-relativistic system. Right? This seems to be a little puzzle. You agree?
Yes.
So that means that now we have to explore what happens when we make a boost, a transformation, a boost transformation. We have to see what Nether Theorem tells us about what is the conserved quantity, you know, and see whether this quantity is another quantity that, you know, that nobody ever thought about. So that's 4. Boosts. Okay, so what is a boost? So a boost, we take each particle and we change it into what it was plus a constant velocity v times t. And time, we don't change. We leave it the same. So that means that the variation of each position vector is this constant velocity v times time. The variation of time is 0. And therefore, the variation of each velocity is what? What is the variation of the velocity of each particle?
0.
0.
Or delta t. Delta t.
Delta t? Delta t is 0. What is the variation of each velocity?
It's B.
Yes, of course it's v. Well, first of all, because if you remember the expression that we obtained for this thing, there was a derivative of this guy, which is 0, because the guy is already 0. And then there is also, you know, the derivative of this guy. If you take the derivative of this with respect to t, obviously it's the velocity. But also, if you think of a system of particles and you make a transformation of reference frame, you know, with a constant velocity v, it is obvious that all the velocities of the particles are going to be, you know, changed by this constant velocity v, which is common to all of them, right? if you move with a constant velocity v relative to a system of particles, in this new reference frame, all the particles acquire an extra velocity, precisely this velocity, capital V, right?
Yes.
So, in one way or the other, this is the conclusion. The variation of each velocity is this constant velocity V. Okay, so now we have to be a little careful here. So let's write down our Lagrangian, and let's be a little explicit. It's going to be 1/2 of the mass of each particle. So I have to do a sum. Huh? That's going to be a sum from I = 1 up to n of each mass times each velocity squared. And so this is going to be the Lagrangian. The Lagrangian is going to be a function of Ri and Ri dot. Let's imagine that this is our, doesn't depend explicitly on time. And then the system, I'm going to assume that the system is isolated, right? So the system is a bunch of capital N particles, and they interact with each other, but they are not in a constant field of any kind. So they just interact with each other. It's like, you know, a group of particles in the middle of a space in the universe, interacting with each other, but completely isolated from the rest. So that means that the potential depends on the distance between two of them. And I'm summing over pairs from 1 to n. So this is a general situation for any potential you want. I don't care. Okay? So they interact with each other proportional to the distance. That's the usual B of R, but in this case, the R is the distance between two of them. And I'm summing over pairs. So that's the 1/2, and that is the I different from J. So I'm sure that you have seen this before. Now, if I make this change of variables, if I make Ri prime is Ri plus Vt, it's obvious that Ri minus Rj prime is the same as Ri minus Rj without prime, because the distance between two particles is the same. I'm shifting both of them by the same amount. So therefore, this doesn't change. The potential does not change. It's the same. Okay? Let us see what happens to the kinetic energy. Okay? So that means that I have to go to the Lagrangian, L of Ri. Okay? And then, whenever it says Ri, I have to replace by the change of variables that I have written here. So that means that I have to write L of, who is Ri? Ri is Ri prime minus Vt. This is how I make a change of variables. If they tell me that Ri is R prime minus Vt, whenever it says Ri, I'm going to put Ri prime minus Vt, exactly this. Okay? All right. So that means that I have to write here 1/2 of the sum from I = 1 up to capital N of Mi, and then Ri prime dot minus V whole thing squared, right? Because I have to take the derivative of this object with respect to time. That is Ri prime dot minus V squared. And then the potential. And the potential does not change because of this little calculation that I did here. So that's a sum I different from J from 1 to capital N of V of Ri prime minus R prime J. So this does not change. Okay. Now, the velocity can be small. right? Because we are only, taking into account infinitesimal variables, right? This is a very small change. But however, in this square here, there's going to be a linear term in V, right? So let's work this out. Let's compute it. Okay, so that means that L of Ri, it also depends on R dot, but I don't care. Okay, it's going to be 1/2 of the sum from I equals 1 up to n of Mi times what? Times Ri prime dot square. So that's the term, the first term, but then there is minus the sum from I equals 1 up to capital N of Mi R prime dot I times V plus the potential. The potential, which I'm going to write down, plus is actually minus, minus. Minus 1/2 sum I different from j from 1 to n v of Ri prime minus Rj prime, like this. So what we see is that the Lagrangian changes into the same Lagrangian of R prime, and R dot prime. So this part is this part and this part. But there is a surprise. There is an extra piece. Sum from I equals 1 up to n of Mi R dot prime I dot V. And this actually, I can also write it like this. Sorry, let me write it again. I can pull out the V. So V times the sum from I equals 1 capital N Mi R dot I prime. So, and this is linear in B, so this is linear in an infinitesimal change. It's not V squared. So it's linear in V, I have to keep it. So there is something going on here, right? So because now the Lagrangian is not invariant. What do we do? The Lagrangian is not invariant, but this is a boost. This is a change of reference frame. It's a Galilean transformation. And we know that non-relativistic mechanics should be invariant under this. We do all these changes of system, whenever I want. So how come that the Lagrangian is not invariant? Is this bad? Is this something we have to worry about?
We only have to worry about this if it changed the action.
Yes, very good. So we saw that exactly that a boost has to be a symmetry because it has to leave the action invariant. Nobody said it has to leave the Lagrangian invariant. Up to now, all the transformations, time translations, space translations, and rotations left the Lagrangian itself invariant, and also, of course, the action. Now is an example in which maybe the action is invariant, but the Lagrangian certainly is not. We suspect that the action has to be invariant because we know that a boost has to be a symmetry of non-relativistic mechanics. So that means that the action has to be invariant. But is this extra piece leaving the action invariant? How do we know this? How do we know?
Because you are assuming that V is small.
No, because we were keeping changes, to first order in the infinitesimal variation. And so this is first order. So this
But
piece has to be there.
Small variation.
Yeah, but this first order, right? And we are always keeping first order. If this was v squared, then I would agree with you, I could drop it, because we said that those we're not going to look at. But the first terms we have to keep, okay? And this guy is first term. V is small, but it's not 0, so therefore it's here. Now, we are facing another puzzle, apparently, which is that the Lagrangian is not invariant. However, the action has to be invariant because we know that boosts are a symmetry, right? How do we know that the action is invariant with this term?
Well, we can write this term of here like a time derivative of something else, and adding a time derivative of some function that depends only on the generalized coordinates and time does not change the action of this Lagrangian, of this
Very good.
system.
Yes, exactly. This is the reason. Absolutely. So the reason is because this thing here is the time derivative of a function which only depends on the positions and time. Absolutely. So who is this function g of Ri and t? It is v sum times sum from I equals 1 up to n of mi Ri prime. And prime because we are talking about prime variables. So yes, here it is. So this is an example of a situation in which the Lagrangian changes, but the action doesn't change because the piece that is added is a total derivative of a function which depends only on the generalized coordinates. In this case, depends only on the position vectors, but not the velocities. The derivative depends on the velocities, but the function itself not. And that's a crucial property, right? So this is the thing that guarantees that the action is not going to be invariant. Okay? Now, so now it seems that things are falling into place. We're finding that boosts have to be a symmetry of non-relativistic mechanics. And this happens because even though the Lagrangian is not invariant under boosts, the action is invariant because the Lagrangian is only shifted by a piece, which is the time derivative of a function which depends only on the generalized coordinates and not on the generalized velocities. In this case, Cartesian coordinates, not the Cartesian velocities. Okay, so now that we seem to be in business, we have to figure out the symmetry test, what the symmetry test tells us, symmetry test, and we'll have to see the conservation law that derives from this, because Noether's theorem is a theorem, so there has to be some conservation law. And maybe we're going to find out that there is a new conservation law that we didn't know about. Okay, symmetry test. What does the symmetry test say in this case? Now we have to be careful, because there is this delta G, right? This was the delta G. We called it delta G. So this is delta G in the notation of the previous slides. So which is the symmetry test in this case? It is derivative of L with respect to R, delta R, plus derivative of L with respect to R dot, delta R dot, equals minus the derivative with respect to time of delta G. And this sum from 1 up to capital N. Now we have this extra piece here on the right-hand side. So we have to be careful. Okay, so let's write it down. Derivative of L with respect to Ri. This we have already said several times is the force times delta Ri. And delta Ri, remember, delta Ri is V times T. Okay, so V times T. So this is Fi times Vt, sum from 1 up to n. Okay, so that's the first term. plus the second term is the sum from I equals 1 up to n. I'm computing now this one. Derivative of L with respect to r dot I. That's mi r dot I. Okay? So the linear momentum. Times delta r dot. Delta r dot was the common velocity, v. Okay? And this has to be minus the derivative with respect to time of delta g. And derivative with respect to time of delta g is minus this thing. So minus and minus is plus velocity times sum from I equals 1 up to n of mi ri dot. Okay? So what do we see? What do we see? What we see is that this term and this term are the same. So they cancel out. And what we find is that v times t times I equals 1 up to n of fi has to be 0. And this means, does this mean something special or not? What is this thing telling us? Right? The symmetry test seems to tell us, since these two terms are the same and they cancel out, that now this whole thing has to vanish. What is this thing? Look at the Lagrangian. This is the Lagrangian. It's a Lagrangian in which we have a bunch of particles moving around, interacting with each other in pairs. What is this sum?
Zero,
Why? Why is it 0?
because these F's are the internal forces of the system and they must cancel out.
Absolutely. Yes. Very good. The sum from I equals 1 up to n of fi has to be 0 because this fi are internal forces. And we know that the sum of all the internal forces in a system cancel out. If you don't believe me, just take the derivative with respect to r of this potential, and you will see how when you sum, you get 0. But we know that had to happen. We know when we're given a potential like this, in which particles are interacting, pairwise, in couples, like this, we know that the sum of all the internal forces is going to be 0. So, in other words, because this is the potential, I could have said, hey, this sum here is 0, and therefore 0 equals 0. So it's a trivial identity. The symmetry test, in this case, the symmetry test is a trivial identity. Doesn't give us any condition at all. In the previous cases, the symmetry test was telling us that either the moment of the forces had to vanish or the total force, acting on the system had to vanish or something like that, right? In this case, it's a trivial identity. We know that for a potential like this, the sum of all the internal forces has to vanish. So therefore, what I find is 0 equals 0. You see what I'm saying?
Yes.
Yes, yes.
So a boost is a trivial identity, in the case of a Lagrangian describing non-relativistic mechanics. Now, we still have to solve another thing, which is conservation law. What is the conservation law? Which derives from this symmetry under boost transformations, which seems to be a trivial identity. Something has to be conserved, but what is it that is conserved? Okay, so I'm going to leave it at this point. So I'll work out the conservation law the next day, but I will let you guys think about it. See whether you can derive the conservation law by just, copying the result from Nether Theorem and interpret what that conservation law is telling you. Whether it's telling you something new, whether it's telling you something trivial, or whether it's telling you something which is wrong. I don't know. Well, it's not going to be wrong because it's a theorem, right? That much you can suspect, right? But let's see whether you can interpret the conservation law which derives from Noether's theorem in the case of boost transformations. Okay? Any questions or comments? Okay, well, if there are no questions, we're going to leave it at this point, and we'll work out this conservation law the next day. Okay? All right. So thank you very much.
Bye.
Bye.
Thank you. Bye.